Hi folks, welcome back to Physics with Captain Rod. I'm making this video here to give a short demonstration of how to apply Newton's second law. So let me chat a little bit about what we're looking at and what we're going to do. So we're going to take a look at this accelerating car here, and I've already kind of started the motion diagram for the car. We're going to assume that this car starts from rest from the position shown. It's going to be accelerating to the left at a value that we'll calculate here momentarily. We're going to assume it goes from 0 meter per second to 20 meter per second over 4 seconds. And we're going to try to calculate how much force is responsible for the acceleration of the car. All right, so for starters, let's chat about Newton's second law. Force equals mass times acceleration. This is a pretty standard Newton's second law type of question. One thing to keep in mind about Newton's second law is this force is always the net force acting on a system. The mass of the car is given in the problem, 1,500 kilograms, so it's going to boil down to finding the acceleration of the car. Now, I don't need to use a velocity graph to do that, but I'm going to go ahead and do so anyway, just because that's consistent with how I tend to teach motion and how I tend to tie it into Newton's laws. So I'm going to go ahead and sketch a velocity graph for the car. And again, remember, the velocity graph describes what the car is doing. So if I go ahead and call this way positive, then these velocity vectors would be getting larger and larger and larger, and they are positive because they're in the direction that I've called positive. Now, at t equals 0, the car's not moving yet, so the first point on the graph is here. Let's see, 4 seconds later, the car is going 20 meter per second. So on my graph here, I can come out 1, 2, 3, 4 seconds. The 20 meter per second, I'm just going to choose to put about here. Now, you are free to put this anywhere you want in your own sketch, but now that I've done that, I've now set a scale. If this is 20, then 10 would be about here, and let's see, 40 would be up around here, and so forth. I'm going to go ahead and connect these linearly, and what that means is I have assumed constant acceleration. Remember that acceleration is the slope of a velocity graph, so when we draw this linear, we're drawing it with constant slope, and therefore we're assuming constant acceleration. All right, and we know that this on the graph here is the 20 meter per second. So the acceleration of this car is rise over run. That's the rise. That's the run. So that acceleration is going to be 20 meter per second over the run of 4 seconds. And we get about 5 meter per second per second. Now, if you want to write that as 5 meter over second squared, that's perfectly fine. Those are the same thing. Those are equivalent. I like to write it like this, 5 meter per second, because I feel that that is a good way to help my brain understand what that acceleration means. After 1 second, this car is going to be moving 5 meter per second. And after another second goes by, it's going to be moving at 10 meter per second. And after a third second, 15 meter per second, and so forth. All right. So we've got the acceleration. We can now find the net force acting on the car. So by Newton's second law, the net force is going to equal the mass of the car, 1,500 kilograms, times the acceleration of the car, 5 meter per second or 5 meter per second squared, either one. And if we multiply this out, I think we're going to get 7,500 out of that. Now let's chat units. So if you remember that force is measured in newtons, that's perfectly fine. You can, I always recommend this. You can always take units at face value. We're multiplying kilograms times meter per second squared. So a perfectly acceptable unit would be just kilogram meter over second squared is perfectly fine. I'll just put or 7,500 newtons, because this is what a newton is. A newton is a kilogram meter per second squared. Now, I didn't ask it in the problem, but if we wanted to, we could also find the total displacement of the car. That would be this distance. That's I traditionally call a delta x. And we could get that from the graph, from this area right here. And although it was not part of my preliminary question here, I'm going to go ahead and calculate it anyway. So the delta x we can get from this area bound under this curve here, 1/2 times 4 seconds times 20 meter per second. If we multiply this out, it's looking like 40 meters. So Anyway, this video is just intended to be kind of an introductory video into applying Newton's second law. I hope that this video has done that for you. Have a great day.